Week 6 announcements. So mini project 2, which is called Class Planner, is released today. So you can get to it by the www.cubstart.com website. It is due on the 1st of July, 1st of April. Now this is not April Fool's, so this is actually due on 4/1 at midnight. So this is not a joke. We're serious here. So make sure you turn it in that by then. And there's two checkpoints. Again, checkpoint one is not, you don't need to submit anything for checkpoint one. It's just there to help you make sure you're on track. So it'll be great if you could complete checkpoint one by next Friday. But of course, we have spring breaks. So just depending on how you manage your time there. So just make sure that you're able to get through those two checkpoints by 1st of April. And this project, again, if you have watched the lecture, especially the NVVM lecture 4, it should be manageable. So regarding for office hours, there will be discussion this week, but for office hours, we're not quite sure. We're still figuring out some of the logistics. So if we do happen to have office hours, we will let you know via Ed. But for now, there'll be no office hours. And if we don't have office hours, please redirect all of your questions to Ed, or you could ask after lecture. And again, if you have any feedback, please let us know in the attendance form. Any questions about logistics? Alrighty. So in today's lecture, we're going to talk about animations. And to start, we're going to talk about the anatomy of an update. How does SwiftUI update your view when there's animation? And then we're going to talk about two types of animations, which is called explicit and implicit. Then we're going to talk about what kind of animation styles there are, which relate to timing curves. And then finally, we're going to end with something called a view modifier called a match geometry effect that allows you to animate two different views together, or how one view could become another view, and how SwiftUI kind of animates between those two views. And we'll take a look at an example later. Okay, so anatomy of an update. So here we have a SwiftUI view. We have an at_state variable, which is called toggled, which is set to or initialized to false. And then in the body, we have the image. And right now we're just displaying a tortoise, the SS symbol tortoise. It is font of size 100, or custom size. And we add a view modifier called the scale effect view modifier. When toggled is true, we want to scale it up by 100%, so it's 2. Otherwise, we want to just keep it as default size, so just a regular 100% size. So, and then we also have a new view modifier called onTap gesture, which when we tap on the view, we want to perform some action. So within this closure right here, we will perform the action. In this case, we're going to toggle on toggled. Again, what this toggled method does is that it flips the value of toggled. So if toggled is false, it flips it to true. Vice versa, if it's true, it flips it back to false. And this is what it looks like. So we have, in our simulator, we have the image of a tortoise. So let's take a look at how SwiftUI kind of does this animation effect when we touch on the view or tap on the view. So here are the states that we have. So toggled right now is false. And then these are the view modifiers in reverse order. So we have the tap gesture, we have the scale effect, which is currently 1.0. We have the font size, which is 50. And then we have the image, which is itself. Let me see if sorry. Oh. Okay. So, all right. So now what SwiftUI does is that it opens a new transaction. So a transaction is something that you create in Swift, and it has metadata of how to basically update your view according to animation. And this is done, automatically for you. So when transaction right now, because we have created a new transaction and we want to change the toggle state to be true, right? When we tap on the view itself. So again, here's the same thing. So what it's going to do is that the transaction is going to go through each of the view modifiers from reverse order. So it's going to go to the tap gesture, and it's going to see if there's anything that we need to do on this view modifier. Well, there's nothing to do on the on tap gesture because that is the originating animation event, right? So there's nothing for us to do. Now, when it comes to the scale effect, we notice that there is something for us to do because the scale effect value has a dependency on toggled, right? So again, when it's toggled is true, we want the scale effect to change to 2 instead of 1. So since there's a dependency, we will update the scale effect to be 2. So now the scale effect has the updated value of 2.0. And then when we go to the font, nothing happens, because there's no dependency on toggled. And then when we go to the image, nothing happens because, again, there's no dependency on toggled. So now the transaction closes and the view is re-rendered. So the view is re-rendered after the transaction. And then here is the new updated value of all the states, right? So scale effect is now 2.0. And then if we tap it again, then toggled will be now false. And then we do the same thing again. But in the prior example, there's no animation because it was we just simply toggled the toggled variable. So how does this work, right? So when does a transaction actually create or happen? So to create a transaction, we could do it via the with animation closure. So when we tap on this view or this image, we will perform the toggle on toggled, but also within this with animation context. And that creates the transaction that we have seen in the prior slide. So again, with animation there. So this is what happens. So when I tap on it, you can see SwiftUI is animating the changes between the scale effect of 200% versus 100%, right? And this is all done just simply by adding this with animation closure. And again, it does the transaction process that I have shown before. So it goes up the view hierarchy chain, and if there's a dependency, it's going to animate accordingly. Now, if we didn't have this with animation, when we tap on it, it would just instantly turn into its larger view. And then when I tap it again, it instantly shrinks back to the regular 100%. So that's the difference. So again, this is the view modifiers in reverse order. We have the animation, we have the transaction here. And in this case, it tracks another metadata, which is this animate that it tracks, and we want to animate it so it's true. So again, it goes down the whole hierarchy in reverse order. Hey, there's a dependency on scale effect. We want to change it to 2.0 now. Now, in this case, it has an animation, and we will animate it accordingly. And then we go down. There's no dependency with the font. Sorry, this should be 100. Sorry for the typo, but there's nothing there. And then now we go back to the image. There's nothing there to do. So that's the main difference with with animation closure. So again, how does this work? So you can see here when the transaction with the animate is true, when it goes to the scale effect, it animates the value from 1.0 to 2.0 via a timing curve. So on the spectrum, you have 1.0 and you have 2.0 on an interval, right? And then between those intervals, you have infinitely many points, right, within that interval. So how does SwiftUI interpolate those changes from 1.0 to 2.0? It's via this interpolation curve, or this timing curve is what we call it. So again, you can think of this, the x-axis as time proceeds, and the y-axis as the value of the scale effect. So again, we start at 1.0, and then we want to end at 2.0 right here. And then as time progresses, the values go from 1.0, 1.05, 1.01, all the way to 2.0 via this curve. I don't know exactly what this curve is, but to me, it looks like a logistic function. This logistic function looks like this curve where the values are, the y values are -1 and 1, but you can shift it, you can transform it, whatever. So, but that is the default Swift animation that does. So if you don't specify what type, so you can also specify type of animation, and we'll just see later, that transforms this curve to something different. So if you want to have more springy effect, this curve might look like, this. It might go up really fast and then go down, or you want to go ease in. So you want to start lower and then accelerate out, or there's different kind of varieties and versions of it. But the different animations will basically change from 1.0 to 2.0, and interpolate between those points. Does this make sense? Questions? Okay. So again, the big idea is that animations are a function of state. So if your state changes, your animation will perform based on that change. So transactions are created and it basically traverses the view hierarchy. And if there's a dependency, or view modifier has a dependency on that change of state, then it will animate it accordingly via some timing curve. And SwiftUI knows how to update and animate views based on information from a transaction that it creates. So just like how we've seen in the prior two examples. All right, so that was how SwiftUI does animations with transactions. Next, let's talk about the two types of animations. We have explicit and implicit. So with the with animation closure that we've just seen, that is called an explicit animation. And here we have a similar view, but the main difference is that now we're not scaling it anymore. Now we're using the offset view modifier to change its position based relatively to its original location. So here again, when toggled is true, we want to offset it by a positive 100 points. If it is not true, then we want to offset it by back by so when it's true, we want to move to the right by 100 points. If it's not, if it's false, we want to move back to where we are. So that's why we have a negative 100 right here. And so this is what it looks like. So we have the tortoise right here, and then and again, let me see. Okay, there we go. So then it animates it to the right and then back. So again, this dot offset is a relative offset. To specify a absolute position within the whole display or screen, you could use the dot position view modifier to do that. Okay. So the with animation closure puts context in transactions, which again tells SwiftUI how to animate changes of state. So the transaction are born at the root view hierarchy and then passed down to all subviews. But we cannot pick and choose which views we want to animate because we have to specify exactly there needs to be some event that occurs. So in our prior example, the explicit animation is when we tapped on the toggled, or we want to toggle the toggled variable. So that's the event that occurred. But this might cause unwanted animations, as we're not able to really specify exactly, where in the view hierarchy you want to do this animation or another animation. So it just does things automatically for us. So if you want a more finer grain control, you could use something called an implicit animation. So in this case, again, this is the example that we have seen before. But now what we changed is that we removed the with animation closure. And now we use this dot animation view modifier instead. So the dot animation view modifier, the first argument is the timing curve that you want. So we specify you want the default timing curve, and then we want to specify what value do we want it to perform the animation based on some change of state, in which case we want to do it when there's a change of state to toggled. And so how this works is that when we click on the tortoise, it will change toggled to be the appropriate value, right? The opposite value. And then since there's a dot animation view modifier here, it will do the transaction for all of the views above it. So it's going to start the transaction here, and then it's going to go up the view hierarchy, like we've seen before. So you're with this dot animation view modifier, you're able to specify exactly where you want the animation to occur. So I could put it here instead, and then I'll do the transaction, via the font and then the image. So you could have more fine-grained control of the animation that you want. Whereas the with animation, it just does the whole thing. So it's just harder to kind of fine-grain it. And it just does the same thing. The behavior from the implicit animation from this example to what we had before is the same thing. Nothing changed. So again, so this is our kind of view modifier hierarchy in reverse order. We have the transaction that we create, but instead of being true at the on tap gesture, our animate kind of metadata is nil. There's no animation, I guess, metadata at this current state. And of course, toggled is true, right? Because since we tapped it, toggled would now be true. So it's going to attach it to itself on the on tap gesture. Well, there's nothing really for us to do here. So it's going to go up. So now we're on the dot animation view modifier. And then it recognizes, hey, there is an animation here. So it's going to update its values to now be true using the SwiftUI default timing curve. And then it's going to carry itself upwards. So, okay, we're on the scale effect. Is there a dependency with toggled? Yes, there is. So we want to animate it with the default timing curve to now be 2. And then it's going to go to the font. I apologize, this should be 100. And there's no dependency with toggled, so we just keep it the same. And then we go to the image, nothing there. So, and then it continues onwards and finishes. So that's the main difference. With the dot animation view modifier, you're able to explicitly specify the origin of where you want the animation transaction to actually propagate. And like again, when it goes to the scale effect, it's going to animate via the default SwiftUI timing curve. So here is another example. We're keeping the implicit animation. We are keeping the scale effect, but here we're also adding a rotation effect. So the rotation effect view modifier allows you to rotate a view based on angles, and you can also specify the angle based on degrees and also radians. So if you need radians, you can do that as well. And also, this is a 2D rotation effect. There's also a rotation 3D effect that allows you to not only specify the angle that you want to rotate the view in, but also the axis. So you also have to specify the axis of the X, Y, Z axis of which axis you want the view to rotate around. So what you could do is that you can make this tortoise and rotate around the Z axis, and it will rotate it like this. So it's pretty cool. So you could see in 3D the view rotating around. But in this case, this is 2D. So when we click on the tortoise, we should expect it to do this. So it's scaling up to 200%, and then it's also rotating at the same time. And also, again, we could achieve the same effect with animation. How do we do that? How do we achieve the same effect with an explicit animation via the with animation closure? What changes do we need to do here? Anyone? It's just 2 changes, two modifications to this code. Yes. Good. And what else? What's the second change or modification we need to do? What is redundant? What is not necessary? Exactly. That's correct. So we basically, just to reiterate, we basically add the with animation closure here and remove this implicit animation view modifier. And it does the same effect. All right, so now we're kind of being more fancy with our animations now. So now, okay, what has changed? So we're still in an implicit animation. We're still using implicit animations, but okay, so we still okay. This still is the same, right? We have the animation default here, and we're gonna start a transaction we have when toggle changed. The scale effect is still the same, but now we have another implicit animation here, and this animation, instead of having the SwiftUI default timing curve, we're going to use the interpolating spring timing curve. So it's going to use a timing curve that emulates a spring. So what does a spring have, right? What properties of a spring have or has? It has, you can specify the stiffness of the spring. You could also specify the dampingness of a spring. So stiffness, I guess you could visualize it as like if you have a slinky, right? And you press it or compress it, how much you could compress it. And the damping is when, I'm not exactly sure, but I think it is when it kind of expands and then it retracts back, like how much it retracts back. So if you take in EEC16B, you do some stuff with the springs, uh, but I don't want to go there. But yeah, it's just basically a math function, basically. So of how it interpolates. And the rotation effect is the same and everything else is the same. So how do we deal with these two implicit animations, right? Well, all right, so we have, again, the first implicit animation, we have the second implicit animation. So what's going to happen is that the default animation style that we've declared here is going to be applied to the scale effect, to this one. Okay, so this animation is going to be applied to this one right here. So the scale effect will be animated via the default animation timing curve. But then the second implicit animation that we define right here, that is now going to be applied to the rotational effect and everything above it. Okay. So we're able to implicitly specify or create subsets of two different animations. So we create two different animations, and those animations apply to different view modifiers. So again, we create a default animation here, and it's going to propagate all above here. And then when it reaches the second implicit animation, it's going to be overwritten. So now we're going to use the interpolating spring timing curve to animate the things above it. So the spring animation style is being applied to everything else above scale effect. Questions? Does this make sense? Okay. So this is what it looks like. So I'll try to replay this again. So as you can see, when it scales up, right, it's used the default SwiftUI animation that we've seen earlier. But when it does the rotational effect, you could see when the spring compresses and then retracts, you can see that kind of, spring-like behavior, right? It kind of overshoots itself and then it kind of undershoots itself and then it kind of oscillates back and forth like a spring. Okay. So that's how you could, granularly specify what animations apply to which view modifiers like this. Does anyone know how we could do the same thing with an explicit animation with animation? You could do that. So you could use with animation to do the exact same thing, but there's some additional stuff you have to do. So does anyone want to give it a shot? What's the first step that we need to do if we want to use an explicit animation? First step. I'm already saying the answer already. With animation, what's the first step that we need to do? Yes, that's correct. So we write with animation here, and then what's the second step that we need to do? What do we remove? Let's just don't look about anything here. Just analyze right here. What do we remove here? Correct. So we're gonna delete this, and then we have with animation. Okay. Now I'm gonna do the rest because it's a bit tricky. So we want to separate this toggle with the toggle right here. So what you do is that you create a new at state that pertains to only the rotational effect. So maybe toggle 2. So you're going to do toggle 2 right here. And then the width animation, okay, so you have the width animation here. And then you do another width animation. And then the width animation also, it accepts the timing curve as a argument. So you're going to do width animation parentheses dot interpolating spring, that thing. And then within the closure, you're going to do toggle 2 dot toggle something. Does that make sense? So you have two states, at states, one for this guy, the scale effect, and one for the rotational effect. And then you have two with animation closures, one with animation closure with nothing passed in. I'd use the default SwiftUI timing curve. And then the second with animation closure with the interpolating spring passed in as the first argument. And within that closure, the second with animation, you're going to do toggle 2 dot toggle. Does that make sense? So two different state variables, one for the scale effect, one for the rotation effect, and then two with animation closures, with the second one with the interpolating spring timing curve passed in as the first argument. Questions? I know that's a bit a lot, but hopefully you could see how you could write something with the dot animation view modifier versus the with animation closure. Cool. This is incorrect. You can, but we cannot do it if we have a single toggled variable. So if we just look at this code and try to use with animation without changing the or adding anything to addition, like without adding additional variable, then we cannot do it. But we can do it if we add another variable and put another variable on the rotational effect. Okay, so if we just, again, this note is just looking at this and saying, okay, don't change the toggle. You can't add additional variables. Can you do it with animation? And the answer is no, because we need this toggle versus this toggle to be separate. Okay, so like I said again, the dot animation view modifier takes in a timing curve and the value that you want to trigger this animation based on this value being changed, right? So it updates the animation context in transactions. It will monitor the value argument and only adds animation context to the transaction if the value argument has changed. And you allow different animation styles on a single view. So like we said again, we've seen how we could scale it linearly and rotate as a spring, and allows more fine-tuned control over what views to animate. So I think the default animation is a linear animation. I'm not quite sure. I need to double check, but I think it's a linear animation. And then of course the rotation effect does the spring-like behavior. All right, so let's talk about animation styles. So this is the with animation declaration. So it's a function, and it accepts two parameters, or accepts, you could pass in two arguments into it. One being the animation that I've talked about. So if you don't specify anything, so you just do with animation and then curly bracket, it uses the default value being assigned to this parameter, which is the dot default timing curve. So this is how you specify, again, default values to parameters. So if I don't specify anything here, it will use the default timing curve. And you can see this is a optional. And then here is a closure. This is our body closure that basically is where we specify the event that we want to happen. And don't worry about the throws and rethrows. Don't worry about that. You'll see that next lecture when we talk about how do we handle API calls. And this is the implicit animation declaration with the dot animation view modifier. And it's pretty similar. Again, you specify the timing curve and also the value you want the animation to happen when the value changes. And don't worry about all this stuff. But these are just kind of the two differences I want to highlight. Okay, so we have another example here. And in this case, now we want to offset the tortoise on the y-axis, so vertically. So here we have, when toggled is true, we want to animate it by 200. And then we want to, when it's false, we want to go back by negative 250. And then the implicit animation that we want to create is with this dot ease out animation curve. And we want that animation to happen when toggle gets changed. So this dot ease out timing curve, it basically starts up fast and then it eases out. Okay, so it ramps up fast and then it kind of eases out towards the end. So you might be wondering, okay, so when toggled is true, why, and then this positive 200, right? We're adding 200 points to the current location of the image. Why is it going down, right? So the reason for this is because the origin of the coordinate plane actually for iOS starts at the top right, left, top right, top left right here. So this is 0, 0. So when we do 200, when we're adding 200, we're actually the y-axis is like flipped. So when we add to the y-axis, it's actually moving downward. So this is the positive y-axis, and then above is negative y-axis. Okay, so it's a bit weird. It's a bit flipped. And then what's even more confusing is on macOS, it's something different. The origin is like on the like where you expect it to be on macOS. But for iOS, it's over here. So it flips around. Also, if you use UIKit, I think it's also different. But we don't need to get into that. But the origin for iOS, I think, is on top origin, top left right there. Okay. So we have .ease out. So these are the default SwiftUI timing curves. So this is what it looks like, right? As time progresses, the value of here, this is the values. So it ramps up pretty quickly and then it kind of tapers out. So it's easing out. And then there's also ease in. And this is what it looks like something. So it's gonna ease, it's gonna start slowly and then it's gonna ramp up at the end. There's also dot bouncy, and it looks like something like this. So it's going to shoot up in the end, at the beginning, and then it's gonna like kind of, and then it's gonna go down, and then it's gonna go up a little bit. So it's gonna simulate kind of the bounciness effect. And it's also dot spring. There's a combination of dot ease in, ease in out, ease in out, I think, that eases in and then eases out. So like the logistic function that I've shown earlier. So it eases in and then, so, starts up slowly and then it tapers out. So ease in out. So again, there's much more. So if you want to do a more linear, so just scales by time progressively, use the dot linear. If you want to do easing, you do dot ease out, ease in out. Spring, there's different spring that you could do by default. So you could do the default spring, you use bouncy, good smooth, snappy. And then you could also customize your spring, like it's an example. with the spring and also the interpolating spring, that a timing curve that we've seen before, that you could specify different properties of the spring, like the stiffness of the spring, the dampiness of the spring. And then if you want to go more local, like if you want to go out and crazy, in iOS 17, there is something called a custom animation protocol that you could conform to, and that allows you to specify a custom animation timing curve exactly to what you want. But that's a bit more advanced. Okay, so we're going to end off today's lecture by talking about this view modifier called matched geometry effect. And this is really great for when you want to synchronize two identical views from, you might have one view in some parent view, like parent view A, and you might have that exact same view in some other view, like parent located in it has another parent, parent B, and you want to synchronize those two views and animate between them. So this is an example. So we have our beautiful OSCE right here as an image, and uh, it's located. Okay, so right now here, oh, okay, well, okay, right now here, this is like, for example, in content view, and then here is like another separate view, like OSCE detail view. And OSCE detail view, as one of its subviews, has this image of OSCE. And in content view, it has the exact same image of OSCE, right? So those two OSCE images are in two separate parent views, if that makes sense. And we want to animate. So now when we display the OSCE detail view, we want to animate that exact OSCE image from content view and animate it to the one in OSCE detail view. Does that make sense? So you can do that with the match geometry effect. So this is how you would do it. So we have an at state variable, of course, because we want to keep track of whether we are showing a full photo or not. And in the body, we have this conditional statement. So if we're showing the full photo, we show the OSCE detail view via this VStack. And the image of OSCE is located in this private variable OSCE title and caption that you don't need to, that we have abstracted it away. And then, so first you need to have a conditional statement. So you got to specify the, I guess, the two different types of scenarios, right? And then here we attach the matched geometry effect view modifier onto the image sorry, the image is right here, OSCE cupcakes. And we attach it to that image. And matched geometry effect has two arguments. It expects an ID. So a unique ID, in this case, it's just a string of OSCE. And then for the second argument, it needs a namespace. You don't need to worry about too much about this. You just specify this namespace using this at namespace property wrapper and this variable, and declare this as a variable and just put it in. And we put the frame and any positional view modifiers after the match geometry effect. So in this case, we're putting the frame of the image afterwards, and anything that we need to do about position stuff. So if you use dot position or if you dot offset, you want to put that after the match geometry effect. Otherwise, it's going to do some weird behavior. So in the else clause, right, this is the same image, but without the OSCE title and caption, right? So again, if we're showing the full photo, we want to show OSCE title and caption. If we're not showing the full photo, we just omit it, right? So in this else clause, we don't have anything there. Now, in practice, you don't want to copy and paste this image, here and also in the first clause, right? First conditional statement. You want to maybe refactor this into a separate variable or something, but I'm just kind of just showing you here. So here we do the exact same thing. So the match geometry effect viewing modifier here needs to match the same one in the previous one. So they need to have the exact same ID and the exact same namespace as we've seen here. So I think that you can have another matched geometry effect with the same ID, but you might need to specify a different namespace, I think. So the namespace is, if my understanding is correct, is sort of like it's like a set. So this I'm transform set, it has unique IDs that it has, right? So if you specify a match geometry effect for another view with OSCI, you're not gonna be allowed to do that because you're in the same namespace, you're in the same set, and you're using the same OSCI. So again, I might be wrong, but I think the you can have OSCI again, but that needs to be in a separate namespace. Yeah, you got to create a different set for that, if that makes sense. Okay. Uh, yeah. Okay, so this is the full code. Again, what you would do is that you will refactor this into a separate view. But I'm just showing you everything so it's just easier to see, right? So if we're showing the full photo, we show this view with title and caption, else we don't. And when we tap on the photo, we will show the one with the title and caption. And what's going to happen again is that since these two images have the matched geometry effect with the same ID in the same namespace, it's going to animate this image here and it's going to animate to the one over here, right? And this one has the size of 150 points for the width and height, and this one has the width of 300 and 300. So it's going to animate between this one and this one, even though they're in two separate conditional statements, right? And we know ooh, from a prior lecture that SwiftUI can know where these things are by its identities, and this is a view. So these images without the match geometry effect, right, are two separate images, right? They have two separate identities. So we could basically bridge the gap between them and animate between this image with this other image based on this match geometry effect. Okay. So match geometry, it matches the geometry of these two images, allowing a smooth transition whenever whenever this view is presented or this view, or vice versa. And like again, this is what it looks like, right? This right here is we're showing this view right here. And then when we tap on it, it will animate to this one. So you can see here, if we didn't have this match geometry effect, it wouldn't animate, right? It would just, show it like, it would just show this instantly without animating the original image here. All right, does this make sense? Am I questions? Okay, good. So this allows you to do really some cool things. It's sort of like how, let's see, it's sort of like how in the App Store on iOS, right? Those card views, when you click on it, it kind of like expands to the full view. I don't know if I could show it. Let's see if I could show it later. Well, I'll show later. Uh, Actually, if I have time, I'll try to show this later. So, let me try to see what I'm talking about. Uh, if it loads or not. I don't know if it loads. Uh, okay, looks like it's not loading, but uh, what I mean is that, like, for example, on the App Store, um, you see that, like, you see like this view right here, right? Here, let me actually try this again. Come on. Uh, okay. Never mind. It is right. Luck is not on my side for today. But okay, so can anyone see my phone? I don't know if you can see it. But you see like this view right here, right? This is like in a list or a scroll view. And then when I click on this, you see it animates into this thing right here. You see that? That's match geometry effect. So you can do these really cool animations or transitions from one view to another view like this, being match geometry effect. Okay. Sorry, I don't know why phone mirroring is not working, but oh well. All right, summarize for today what we learned. We learned that animations in SwiftUI are a function of states, and we create animations via transactions. And a transaction carry metadata about the new state and animation properties, such as the timing curve. Explicit animations happen when there's a change of an event that happened, and it will animate all views affected by the state change up the view hierarchy. Implicit animations give you more control because you can specify multiple implicit animations between different positions in the view hierarchy. And as the animation occurs, it will override the one prior so that the subsequent view modifiers will be applied or animated with a different timing curve. And then we learned at the end that we could use dot match geometry effect with a unique ID and also a namespace so that you could smoothly transition between the size and location of a view to another exact view in two different parent view contexts. Or it doesn't need to be a parent view. You could also use this if else statement. And that does the job as well, right? And again, you could do it with two different parent views, or you could transition it via the if else conditional statements. Because if one condition is true, then SwiftUI will basically destroy that view and then render the other else clause, right? The view of the other else clause. And if you want to look into more complex animations in iOS 17, there's something called a keyframe animation where you can specify the exact points and values via like a keyframe. Like for example, if you edit in iMovie or something, you could specify those points.